Hi there, I'm Ken Benoit. I'm going to be presenting a paper today, which I call Beyond Bag of Words, Detecting and Using Meaningful Multi-Word Expressions. Here's the outline of what I'm going to discuss. First, I'm going to characterize what the problem is. Second, I'm going to identify what are meaningful multi-word expressions. Third, I'm going to talk about how to detect these. Fourth, I'm going to talk about how we can use these to improve bag of words studies. And then fifth, I'm going to talk about how this is done. Here's the problem, first of all. The problem is this. There are lots of multi-word expressions in domain-specific text. And when we use the tools of quantitative text analysis for doing analysis, we are very usually dealing with domain-specific text. Domain-specific terminology is rife with multi-word expressions, up to 40%. This is a list of words and also an illustration of the problem with tax words. So if we were looking at economic language and we were looking at taxes, if we were speaking German, which for historical reasons we're not, you would take multi-words and you would put them all together and make one monster word. But in English, we don't need to do that. We keep them in separate words. But if we were to use bag of words to tokenize the expressions on the right, we would no longer know the association of the specific type of tax with the word tax. Tax would just be put into the mix. And as you can see in the third column, if we were doing a political analysis, these taxes have different implications. Some would be associated with the left, and some would be associated with the right, and others would just confuse us, like the employer's national insurance contribution. So how do we do what the Germans do, which is to compound these things so that we have one unique token in a bag of words versus separating up these multi-word expressions from and disassociating them from their context? Here's the worst case. This comes from German, to pick on the Germans. It means the law concerning the delegation of duties for the supervision of cattle marking and labeling of beef. And in German, they just have one word for this. And I think if you Google this, you can find someone to actually pronounce it. The other problem with this, of course, is that bag of words is the wrong model for many of the analyses that we would like to use. It violates an assumption that we would require in statistics called conditional independence, which means that if we're applying some machine learning model or a scaling model or something that has some statistical foundation, the probability of observing one word is changed by the probability of observing a second. And that is not, that violates the notion of independence. This can cause, among other things, the underestimation of uncertainty because we are overconfident because we are looking at data that is not independent, but data that's basically doubling down. It also can conflate different feature associations, which leads to bias. So if we observe the word national, it's really different whether we're talking about national insurance, national security, or national socialist. Double weighting also affects averaging-based models for two-word terms. So if we were looking at European Union and we were using some sort of averaging method where relative frequency reinforced some tendency, and we were to observe European and to observe Union, instead of counting this as a single term, we'd be double counting it, and therefore it could affect scaling estimates. How do we solve this? Well, the first thing I'll tell you is the way not to solve it. The way not to solve it is to use a brute force solution. Just include all bigrams, include all trigrams. This will effectively multiply your corpus, double it, triple it, and you'll have you'll aggravate the problem of sparsity to an absolutely extreme degree. We would prefer a targeted approach. So how we solve it is, number two, to determine a functional method to detect these multi-word expressions in corpora. And I have here political corpora because in the application paper, we're dealing with political text as a first stop, but it could be, as I'll explain, any domain. We can do this through association measures. Statistically, which words are more likely to occur in sequences? Those are most likely, those are our statistical candidates for multi-word expressions. We can do this through filtering. So we don't, probably not interested in stop words. And we can also do a lot of targeting through looking at particular parts of speech, which make up what we would consider meaningful or significant multi-word expressions. And also through predictive methods. We can use human annotation, and this human annotation can tell us the multi-word expressions that we would like to have our method predict. We can then apply the method to a massive corpus, and use this to extract and discover multi-word expressions, and in essence, compile a list of multi-word expressions. And in future applications for a particular domain, we'll have in essence a dictionary of multi-word expressions, and we can use these to find in the text and do the compounding that the Germans did in the first table, which is to create a single word out of sequences of words. And this would not require the discovery step, which is going to be computationally intensive. And then, of course, we need to show that this makes a difference. In other words, why did we bother to do this? Let me tackle the first question about, but this is the next on the list. What are meaningful multi-word expressions? Well, we have to apply two sets of criteria. One is linguistic and one is statistical. Linguistic criteria: a meaningful multi-word expression is a sequence of words that can have meaning as a unit rather than as a string of individual words. So it's a phrase that we would recognize as a candidate for being compounded if our language were a compounding language. A second criterion is statistical. It's a series of tokens whose co-located occurrence is not something that occurs by chance. Our focus in the paper is on a statistical method, a new statistical method for determining multi-word expression candidates, and using then linguistic criteria to filter out the ones that are meaningful. So we use a combination of these, but it starts with a statistical definition. In essence, it's this: based on the co-occurrence of words, a sequence of k successive words is a candidate for a meaningful multi-word expression if it occurs sufficiently often in the corpus. So it's based on frequency. This is not a sufficient definition, but it's one that we consider necessary for an expression to be a multi-word expression if in the linguistic sense, in our substantive sense. If you're familiar with linguistics, you're probably familiar with this topology or this taxonomy from SAG et al. 2002. They talk about different categories of multi-word expression. There are fixed expressions, semi-fixed expressions, and institutionalized phrases. And there are a few subcategories here. We put some in examples here in the right column. For example, New York City should never be split. That should be considered a proper name. There are also foreign terms. There are some fixed phrases like banana republic, a phrase you might have read in the news recently. Semi-fixed expressions such as idioms, fat cats and pork barrels. Then there are things like member of parliament and phrases like alternative minimum tax. And there we get back to some of the economic terms. There are criteria that we have, substantive criteria from linguistics for what is meaningful. So a phrase has to be fixed. So hung parliament, it's something that we don't unpack to say a parliament that is hung. There's also things that orthographic lexicalization. Sometimes we have words that have been compounded or that will be compounded. There's non-compositionality. So if you're trying to figure out what first lady is, and it's an example I'll use later, it's not the first in the sequence of ladies. It means something unique. It means the wife of the president. And then there are proper nouns. So proper nouns almost always indicate multi-word expressions, such as Supreme Court of the United States. That's a proper noun. And that actually gives us an easy way, because with a lot of trained language models, we can identify entities and proper nouns. And those are things that we would pretty much always want to keep. We would never want to split those. Now let's turn to the statistical definition. I'm going to give you the very abbreviated approach because this is supposed to be 15 minutes, and I don't want to tax your cognitive, I don't want to cause any sort of stress by trying to pack in too much here, and it would be boring anyway. So it wouldn't be a good presentation. So let me just give you the essence. We have a fixed sequence of K. K words would be the length of our multi-word expression for which we're searching. For each candidate expression, we're going to look at every K word sequence that appears in the corpus. So it's a computationally intensive procedure. And we're going to have to calculate the value of this statistic. We're going to define a statistic theta in a way that higher values of this statistic are regarded as stronger evidence that we're dealing with a multi-word expression. Then by calculating this for each sequence, we can look at the expressions with the highest values of theta and then make decisions about some cutoff below which we will ignore and above which we'll consider them as the candidates for future investigation, probably for human review and decision making. Once we have that list and we've agreed on it, We can then treat these expressions in subsequent text as single words. We can perform the compounding using some mechanical tool. So the question is, how do we choose this statistic theta? There are a lot of possibilities in the literature, especially for two-word multi-word expressions. We have come up with a generalized measure that draws on classic models from categorical data analysis, in particular log linear models. Our statistical definition can be given in terms of a single quantity, parameter we call lambda, which is the highest order interaction parameter in a saturated log linear model in a k-way contingency table that is defined by the appearances of this expression and its sub-expressions, so subparts of it, in the corpus. This is a way to not have to fix the analysis for a given length of k, but also to deal with sub-expressions. So if we had something like alternative minimum tax, we would be able to tell the difference between that as a three-way phrase versus, say, occurrences of just minimum tax. This parameter lambda can be used as our statistic theta. So how do we do that? How do we apply this to detect them? Well, a little bit of background on how this is done in a classic sense. If you think that we're looking at bigrams or two-word sequences, we essentially have a 2-by-2 table. We have the occurrence of the first word, and then the occurrence of something that's not the first word. Then we have the occurrence of the second word, and then the occurrence of something else. What we're looking for is this first cell, this N11, is typically where the focus is, because this is the occurrence of the first word followed by a specific second word. And we mean this generically, so we're having to form this 2-by-2 table for every single pair of words that could occur in the text. And using association measures, we can figure out whether this occurs by chance. The classical measures are the very simple things you would have learned in Data Analysis 101 for categorical data, such as the likelihood ratio statistic, or G-squared, which is the paper by Dunning, where he identifies this as one of the ways to detect multi-word expressions. A second statistic is Pearson's chi-squared statistic, which is similar. It looks at the divergence between what would be expected to occur by chance and what has actually occurred. There are some other measures that I'm not going to go through, but this is the idea in the classic way. The problem is that these don't generalize to lengths greater than 2. So that was one of the first problems. The other problem is they have certain tendencies when it comes to very low frequency words that we think our measure avoids. The other thing that you can do to detect the meaningful part is to impose the linguistic criteria of looking at part of speech filtering. With the exception of some middle word prepositions, such as members of Congress, where of is a preposition clearly, most of our applications, following a paper by Justison and Katz, found that the meaningful multi-word expressions consisted of noun and adjective sequences. So we can pretty much ignore the other parts of speech except for the ones with prepositions in the middle. We also consider anything that is a proper noun to be a meaningful multi-word expression. So Scottish National Party, for example. And that's nice because if we have some advanced tagging models such as SPACY or Stanford Core NLP, we can identify named entities and then just consider those to be multi-word expressions without doing even statistical recognition. So here's the details of our implementation. And I hope this isn't too rushed, but I just don't have time to go into much more detail. Suppose we examine for a corpus of text. We've turned this into a data set of k-word sequences. So we have these sequences as Z1 through this ZN star. Our target expression is going to be looking for candidates like X1 and X2. So we'd be looking for a sequence of 2 words. Generically, we call it X1 and X2. And we would compare this to the sequences that we observe in this sequence Z1 through ZN star in the corpus. And we would summarize this in a contingency table, similar to the one that I showed before. We could denote the dimensions of this table as the probabilities that we would write as this P sub C1, C2, and C1 and C2 would be 0 and 1. These are occurrences or not occurrences. These are going to be probabilities that neither word of this expression ZJ matches the corresponding word of X1 or X2. We call this probability P00. The first word can match, but the second doesn't. This would be P10. Second word matches, but the first doesn't, which is P01. And then that we have the golden cell, the one that would actually be first, that the observed expression matches it exactly, this P11. Well, If we consider it that way, and this does generalize to longer tables, then we can write the log linear formulation as a model that has these expressions lambda in it for each of these combinations. And our focus is on this last one, this lambda for the C1, C2 equals 1, where this lambda is equal to the log odds ratio, which describes the association between the two dimensions of the table, which is our first and our second word. When lambda is 0, these words x1 and x2 occur independently, and in the corpus, if lambda is greater than 0, then it means evidence that words x1 and x2 occur together more often than can be expected. And this can be used as our measure directly of theta. I hope that wasn't too boring and too detailed, or I also hope that it wasn't insufficiently detailed so that I didn't explain it very clearly. But it not only works, we've already implemented it in code, which you can use. So what are the next steps? Well, we're going to do a massive mining of corpora, and we're working on initial application on political corpora, political and economic corpora. We're going to use some human verification to do this detection to see if it matches what humans would consider meaningful. The payoff is going to be a giant word list of multi-word expressions that we can use for pre-processing text. So we're going to basically provide a dictionary of multi-word expressions for a specific domain and say, in future applications to improve your predictive models, your topic models, all other statistical models based on text, first do this compounding of your text using our dictionary. And if you want to add new phrases to it, of course you can. But we were going to have mined this quite extensively to do that, so that this mining step is not necessary. When we're talking about billions of words, we're going to be mining them for multi-word expressions and verifying them. And once we have this method, we can also, of course, let people discover multi-word expressions from their own corpus. So how do we use these? I hinted a little bit there. Now I'm talking about a tool which I developed. This is a set of tools in R built around a package called Quantita. Quantita stands for the Quantitative Analysis of Textual Data. That's the acronym. And I'm showing you this in R. I know a lot of you will probably be using Python. It's fine. I used to do that until I developed this R package, which I think is better. So let's take a sentence like this one here. The United States ended its fiscal year with funding for Social Security and healthcare. Well, we would be wanting to compound United States, maybe fiscal year, Social Security, healthcare. Those would definitely be multi-word expressions. So when we tokenize this, we get something that looks like the following. We can then compound this with some multi-word expressions, which are this vector here calls, which are actually a list of multi-word expressions. And once we've applied this compounding stage, if someone were to give us this list, and I'll show you how to develop that in a second, then it turns our bag of words into bags of phrases. And these bags of phrases would be multi-word expressions compounded to make a single token. And once they've been, and here we've used the underscore operator just to tell us that these were originally 2 words, then we can treat this as bag of words, even though it's actually not bag of words. The compounding function is smart enough not to compound across punctuation boundaries. So we would have things like 1, 2, 3, over here, 1 and 2 are compounded, but not 3 and 4 and 5. The alternatives would be to use some named entity recognition. And here I've done this for the State of the Union corpus. And if you run this through something called Spacey, and we extract the named entities, then we can see that these are automatically recognized from this trained language model, and we could use those. So that's something we'd also recommend. There's just some more examples. These are noun phrases, actually. So these may or may not be like the last year. That's not something I would consider a meaningful multi-word expression, but the Soviet Union, I would. So how are we going to deliver this practically? Well, we call this multi-word expressions for the masses. The deliverable for this project, and we're not done with this yet, is to develop domain-specific dictionaries that can be used for pre-processing in the same way that off-the-shelf stop word dictionaries can be used. Examples would be legal texts, business text, economic text, maybe finance, maybe medicine. The nice thing about this is that there are no penalties for being inclusive or comprehensive. For example, if I supply in this dictionary multi-word phrases, stare decisis. That's not going to occur in non-legal text. So if it's not found, it's not going to adversely affect results. It's just not going to do anything. Very rarely, it's like having stop words that you don't have in the text. If you don't remove a stop word from an alien language because it's not found, it's done no harm. Now, it can do harm if there are what we call false positives. So if we remove something that shouldn't be removed, that's bad. But this almost never happens. So you almost never have something like, if we were to say first lady is a multi-word expression, the first lady, comma, was happy over the successful Mars landing. That refers to the president's wife, but she was the first lady to make a successful Mars landing, in addition to using an antiquated reference to female gender. That's an expression that really wouldn't occur, maybe not outside of a golf club or something like that. And any damage from these false positives is likely to be very less than the damage from ignoring multi-word expressions. Would also, I would say it's going to do a lot more good than it could possibly do harm. What are the tools for implementing this? Well, in Quantita, we've got a discovery tool called TextStat collocations that applies our log linear method for multi-word, multi-variable length multi-word expressions. It will discover them and score them according to the statistic lambda. We have a function called TextStat compound that can take those and then turn your bag of words into bags of phrases, targeted phrases. We also have dictionary methods and lookup methods that are optimized for multi-word expressions. So you can have dictionaries consisting of multi-word expressions. These are also very efficient. They're written in C++ for the heavy lifting. They're parallelized, and they integrate very nicely with natural language processing tools such as Spacy, which is Python library. Thank you very much. I'll be happy to answer questions at the event, and I hope you enjoyed this and that I didn't go into too much boring detail. Thank you very much. Bye.